Before we move into planning, I want you to keep one idea in mind. Reservoir modeling is successful when it is fit for the decision you need to make. A model built for early volumetrics is different from a model built for detailed development drilling or simulation history matching. So now we move into model planning, the stage where we define what good means for this model. Model planning is where we reduce confusion and waste. Before we open modeling software, we need to ask fundamental questions. What is the purpose of the model? What data do we have? What is the uncertainty level? And what is the timeline? In real projects, teams often have limited manpower and limited time, so planning helps decide how detailed the model must be and where simplification is acceptable. This slide highlights a powerful planning framework. Align the business objective, the input database, and the conceptual model. If these three are consistent, your modeling work becomes much more efficient and much more defensible. This slide asks the most important question in modeling: why are we building this reservoir model? The correct answer is never, because we have software. We build the model to answer decisions, such as estimating in-place volumes, selecting drilling targets, evaluating connectivity, understanding fault compartmentalization, or preparing a simulation model for forecasting. The business objective defines what accuracy level we need, what uncertainty we must quantify, and which data types matter most. When students learn modeling, I want you to practice stating the objective in one sentence, because that sentence becomes the North Star for all modeling choices. Here we see typical objectives and their implications. If your goal is in-place volumes, then geometry, net to gross, porosity distribution, and contacts are central. If your goal is recoverable volumes and production profiles, then connectivity, permeability architecture, relative permeability assumptions, and uncertainty become more important. If your goal is an optimized depletion plan, you must consider well placement, injection patterns, pressure support strategy, operational constraints, and economics. The teaching message is that different objectives create different modeling scopes, so you should never build a one-size-fits-all model without clearly defining which decisions it will support. This repetition is useful. Good modeling is not only geology, it is project management and engineering decision support. At this point, you should feel that modeling begins with planning and data collection, not with gridding. Now we transition to the second pillar, the input database. This is an excellent question because the honest answer is, enough to support the objective, but not so much that you waste time without improving decisions. Reservoir modeling can use seismic, well logs, cores, outcrop analogs, thin sections, biostratigraphy, production data, and existing models. The key teaching point is scale. Seismic constrains large-scale geometry, wells constrain vertical details, core constrains pore scale truth, and production data constrains dynamic connectivity. The modeler must decide which data sources are most influential for the objective and prioritize those, while documenting what is missing and how that missing information increases uncertainty. Geophysical data, especially seismic, often forms the backbone of the structural framework. Seismic interpretation provides horizons and faults that define the main reservoir shape. When available, seismic attributes and inversion results can support property trends such as impedance variations that correlate with lithology or porosity. Time-lapse seismic, if the field is mature, can even constrain flow behavior and compartmentalization. The key teaching point is that geophysics provides large-scale continuity and structure that wells alone cannot reveal. Petrophysical data usually comes from well logs and core. Logs provide continuous vertical measurements, gamma ray, density, neutron, sonic, resistivity, that allow us to interpret lithology, porosity, and saturation. Core provides direct measurements, porosity, permeability, mineralogy, thin sections, and sometimes special core analysis that calibrate the log interpretation. In modeling, wells are the primary conditioning points for property modeling. A good modeler treats wells as anchors and recognizes that uncertainty grows as we move away from well control. Geological data includes reservoir zonation, stratigraphy, sedimentology, and an understanding of depositional environment and diagenesis. This is what allows you to build a realistic conceptual model of architecture, channels, shore faces, bars, turbidites, carbonate platforms, and not just interpolate properties mathematically. Geological reasoning tells you what shapes are plausible, what stacking patterns make sense, and where barriers or baffles likely exist. Without geological input, property modeling becomes a purely numerical exercise that may produce visually smooth but geologically incorrect results. This slide is very realistic. Reservoir modeling projects often face data errors, mixed file formats, huge data volumes, software upgrade issues, and legacy paper records. In practice, a surprising amount of modeling time is spent on quality control, checking well headers, depth references, unit consistency, coordinate systems, datum definitions, log merges, core depth shifts, and seismic time-to-depth conversion assumptions. A strong teaching message here is that modeling is only as reliable as its data foundation. If you skip database QC, your final model may look professional but be fundamentally wrong. Now we return to the planning triad again because we have covered objective and database, and we are ready for the third pillar, the conceptual model. This is where we translate geology into modeling rules, how units connect, how facies are expected to distribute, and how heterogeneity should look between wells. The conceptual model is the synthesis of our best reservoir understanding using all available subsurface data. It is often expressed using drawings, cross-sections, maps, and qualitative descriptions before digital modeling begins. Conceptual models can also use analog fields and outcrops to guide architecture when data are sparse. The purpose is to provide a geological compass that prevents the digital model from becoming a random interpolation. A good conceptual model answers questions like, what depositional system formed this reservoir? What are the expected flow unit shapes? And what heterogeneities control connectivity? This slide teaches an important modeling truth. Correlation choices strongly influence connectivity and flow. Chronostratigraphic correlation emphasizes time-equivalent surfaces and sequence boundaries, while lithostratigraphic correlation emphasizes lithology continuity. Picking the correct correlation is not only an academic argument, it can change the connected sandbody network and therefore predicted sweep efficiency and production behavior. In teaching, I recommend you emphasize that stratigraphy is a driver of flow architecture. And this is why reservoir modeling must respect sequence stratigraphy and architectural elements. This slide highlights a valuable quality check. When you use concept sketches as modeling guidelines, you should compare the digital result with the original concept to see whether you actually captured the intended architecture. For example, if the concept says channel belts should meander and connect in a specific direction, then the digital facies model should reflect that. If the result looks geologically unrealistic, it's often a sign that modeling parameters or assumptions need revision. This comparison practice helps prevent models that are numerically correct but geologically meaningless. This slide emphasizes that geology and petrophysical properties are linked. Facies in depositional environment influence porosity and permeability through grain size, sorting, clay content, and diagenesis. For example, a high-energy shoreface sand may preserve good porosity and permeability, while a lower-energy muddy facies may be a barrier. Diagenesis can further enhance or destroy quality. In modeling, it is best practice to condition petrophysical modeling on facies, because that produces property distributions that follow geological reality rather than purely statistical smoothing.